Good morning, good afternoon, or good evening, ladies and gentlemen. Welcome back to Unit 8A. Today we're going to be jumping into Lesson 8.2, which is all about charging objects. But before we do that, it might be a good idea for you to go back and review Lesson 8.1. Some of the concepts that we learned in that lesson will be applied today. Alright, so the first thing we need to do is talk about the fact that all objects are made of atoms, and some of the things we're going to talk about for the next minute or so will probably recall what you learned in your chemistry class. You might remember that atoms are made up of protons, neutrons, and electrons. Protons are positively charged, so I color them red, and they're located in the nucleus of the atom. Electrons are negatively charged, that's why they're colored blue, and they orbit around the nucleus in these shells. Now, if we were going much deeper into this, then we would talk about how many electrons are located in each shell, but that's not really important for the purposes of this lesson. So all you need to remember is that protons are in the center of the nucleus and electrons orbit around the nucleus in these shells. Now, if an atom is electrically neutral, then the number of protons is equal to the number of electrons. The atom also contains neutrons, but it doesn't really matter how many neutrons the atom has as far as whether it's neutral or not. All that matters is that the number of protons and the number of electrons are the same. Now, because the protons are locked away inside the atomic nucleus, their number doesn't really change, except in the case of nuclear reactions, but that's a whole other story. The number of electrons, however, can increase or decrease. Atoms can gain electrons from other sources, or they can lose electrons. So once again, the number of protons is pretty much a fixed number, but the number of electrons can increase or decrease. Whenever an atom gains one or more electrons, then suddenly it has more electrons than it has protons, and as a result, it has a net negative charge. For example, if an atom with 3 protons and 3 electrons were to gain 1 electron, then it would have a net negative charge equal to 1 elementary charge. It would have 1 negative elementary charge overall. On the other hand, if the same atom were to lose one of its electrons, then it would have a net positive charge because it still has 3 protons, but it only has 2 electrons, so one of its protons is not canceled out. Now, not all atoms are equally likely to gain or lose electrons. Some atoms are more likely to gain electrons and others are more likely to lose them. This tendency to gain or lose electrons can also be affected by what other atoms our atom is bonded to. Now, large objects are made of smaller atoms, so large objects can also gain or lose electrons. The atoms in them can gain or lose electrons, and those electrons can then travel to or from other objects. And just like with an atom, if a large object loses electrons, then it becomes positively charged, and if a large object gains electrons, then it becomes negatively charged. But how can we charge an object? With a credit card, of course. Seriously though, there are 3 ways to cause an object to get an electric charge. The first is called friction. We'll talk about this in just a moment. The second is called conduction, and the third is called induction. So let's talk about these 3 methods of charging an object and see what each one involves. We'll start with friction. Now, friction is easy enough to understand. If you know what friction means, it's whenever 2 objects rub against each other. And when this happens, electrons from one object can actually be scraped or rubbed off onto the other object, and that will cause both objects to become charged. The object that loses the electrons will become positively charged, and the object that gains the electrons will become negatively charged. Neither object needs to be charged beforehand. This can happen when 2 neutral objects rub against each other. And the objects will end up with opposite charges because one object loses electrons and the other gains them. One will become positive and the other will become negative. An example of charging by friction is when you walk across a carpet wearing your socks. you build up an electric charge on your body, and you can become aware of that electric charge if you touch a metal doorknob. If you've ever touched a metal doorknob after walking across a carpet and you get a little jolt or a little shock, that's all the electric charge that is built up on your body exiting very quickly through that one point of contact, and it feels like a little burst of heat. This child has also built up an electric charge from sliding down the slide, and you can tell that he's charged because his hair is standing up. When your body builds up electric charges, many times the electric charges will travel to the furthest places that they can get away from each other, which will be the tips of your hair. And then because like charges repel, your hair will stand up and try to get away from all the other hairs. There's a useful chart called the triboelectric series, which compares how easily certain materials will lose or gain electrons. Here's how it works. The higher an object is on the series, the more likely it is to lose electrons and become positively charged. The lower an object is on the series, the more likely it is to gain electrons and become negatively charged. So if you pick two materials on the series and rub them together, then the one that is lower on the series will most likely be the one that gains electrons, and the one that is higher on the series will be the one that loses electrons. So for example, if you blow up a balloon, which is made of rubber, and you rub it against your hair is likely to lose electrons because it's closer to the top of the series, and the balloon is likely to gain electrons because it's closer to the bottom of the series. So here's a skill practice question, but it doesn't require any mathematical skills. It just requires being able to interpret the triboelectric series. So suppose you pull a polyester t-shirt over your head, after which you notice that your hair is standing on end, indicating that your hair became electrically charged as it brushed against the polyester. Using the triboelectric series, determine which material, hair or polyester, became negatively charged and which became positively charged. Again, this is a simple matter of seeing which material is closer to the top and which is closer to the bottom. Well, we've already established that hair is fairly close to the top. There are only 3 materials that are more likely to become positively charged than hair, and polyester is all the way down here closer to the negative end. So the polyester t-shirt will pick up electrons and become negatively charged, and the hair will lose electrons and become positively charged. The next method of charging is called conduction. Now this requires that at least one of the objects already has an electric charge. Perhaps it became charged by friction when touching another object. And then it touches an object that is either neutral or may have an electric charge of its own. It doesn't really matter, but it can transfer some of its charge over to the other object. So the difference between friction and conduction is that friction can occur when neither object has an electric charge, and in order for conduction to occur, one of the objects must already be charged. Now it turns out, whenever one object charges another by conduction, both objects wind up with the same charge, which is the average of the object's initial charges. So let's take a look at this skill practice question with that in mind and see if we can solve it. It says metal sphere A has a charge of positive 40 millicoulombs, and metal sphere B is neutral, which means its charge is 0. They are allowed to touch. What is the charge on both spheres after touching? Well, the charge on both spheres will be the average of the two spheres' charge before touching. So sphere A had a charge of positive 40 millicoulombs. And because this is not a Coulomb's law problem, we don't have to change that into regular coulombs. We can leave it in millicoulombs. And sphere B had a charge of 0 millicoulombs because it was neutral. And then to find the average of those two numbers, we simply add them together and then divide the result by 2. And 40 plus 0 is still 40. And then we divide that by 2, so both spheres after touching will have a charge of positive 20 millicoulombs. So that's another difference between charging by friction and charging by conduction. In charging by friction, the spheres would end up with opposite charges. So for example, sphere A would be positive 20 millicoulombs and sphere B would be negative 20 millicoulombs. But when we charge by conduction, if one of the spheres starts off neutral, then they both wind up with the same charge, with like charges. So they both end up being positive in this case. Here's another skill practice problem involving charging by conduction. It says metal sphere A has a charge of positive 40 millicoulombs, so similar to the previous problem, and metal sphere B has a charge of negative 20 millicoulombs. They are allowed to touch. What is the charge on both spheres after touching? Our technique for solving this problem is going to be the same as before. We're just going to calculate the average of positive 40 and negative 20. So on top, we'll add positive 40 millicoulombs, and it is not necessary to convert to coulombs as long as both charges are millicoulombs. We'll add negative 20 millicoulombs, and on the bottom we will divide by 2. Positive 40 plus negative 20 is going to be positive 20 millicoulombs on top, divided by 2, so both spheres will wind up with a charge of positive 10 millicoulombs, which is the average of positive 40 and negative 20. The last method of charging is called induction. Now, induction is a method of charging where the two objects don't actually have to touch. That's how it's different from charging by friction and charging by conduction. No actual contact is required. Now, like with conduction, one of the objects must already be charged. But what happens is that as you bring the two objects together, the second object is grounded. So let's take a look at a diagram. Maybe it'll make better sense. Here's our object that is going to be charged. We bring another object close by that is already charged, say this rod, which carries a negative charge. As a result of this negative charge, the charges in the sphere here will separate, which is to say all the negative charges will be repelled away to the opposite side of the sphere, leaving only positive charges on the side of the sphere facing the rod. Now the sphere is connected by a wire to the ground. The ground is essentially an infinite source of positive and negative charge, so it's a place where charges can always be stored or can always be taken from. It's not really infinite, but it's so huge that for all intents and purposes we can think of it as being an infinite source of charge. So, the sphere is connected to the ground, and the negative charges, which are repelled by the negative charges on the rod, are driven down the wire and into the ground. Now we disconnect the ground wire, leaving the sphere with a net positive charge, and then when we remove the negatively charged rod, the sphere will maintain its positive charge as long as it is not allowed to directly connect to the ground. This is called charging by induction. So unlike friction or conduction, the charged rod never has to directly touch the sphere. And unlike in conduction, the sphere winds up with an opposite charge from the rod. The rod was negatively charged in this example, and the sphere winds up being positively charged. If the rod had been positively charged, then the sphere would wind up being negatively charged. And that's going to be it for lesson 8.2. I thank you very much for your time and attention. As always, please hop on over to Google Classroom where there will be a very short assignment to test your understanding. And come back tomorrow when we will be going into lesson 8.3, which is all about electric potential. Yay! Until then, thank you very much. Keep taking care of yourself. Keep washing your hands, ladies and gentlemen. And I will talk to you tomorrow. Bye.